Hello everyone, in this video we are following chapter F4.7 Integrating Time Series with CCDC. This is from the book Cloud-Based Remote Sensing with Google Earth Engine. In this video we are trying to attempt to go through this chapter, and briefly we are trying to study some concepts and some codes. We begin with the definition of time series. The time series is the sequence of observations taken sequentially in time. An intrinsic feature of a time series is that typically adjacent observations are dependent. Time series analysis is concerned with techniques for the analysis of this dependency. In remote sensing, we also have this similar idea of the time series. In remote sensing, we collect the radiation from the surface of the Earth. We get the consecutive measurements, and we analyze and characterize the surface based on those collected radiations. And when these radiations are collected in continuous basis, this provides us the multitude information about the surface, and it even leads to understand the changes occurring in the surface. The advantage of current time is that we have the cloud computing platforms such as Google Earth Engine. And this algorithm CCDC is different from LandTrainer in that basis, where CCDC collects all the available clear observations of the year. So it tries to collect any changes within the year, unlike LandTrainer, which tries to get only one clear image from a single year. And CCDC requires computational demands, so it is computationally demanding as it tries to observe all the observations within the year. And what are the spectral changes? So spectral changes are the structural breaks in the time series in the pixel level. So we get some periods of unit reflectance, and then there is some kind of change, and then again we get some periods of unique reflectance. So this continues. So based on that, there is some kind of temporal segmentation. The segmentations are done according to the period of the unique reflectance. And we also feed the harmonic regression models, where we get the coefficients, and those coefficients can predict the future observations. And if the residuals exceed some statistical threshold, we consider that as the changes. So in each change, we feed the regression model, and it continues until the end. So the authors have provided with the link here in the F4.7a. We get this link, and when we go to this link, we get this interface, and this allows us to use this latitude and longitude to see this chart. And what we see here is that we have a straight trend in certain period of time till 2006, after which we can see that there is some kind of changes. So the values are generally larger, and this is case for the SWIR band. So the surface reflectance have changed beyond 2006, and there is also some kind of seasonality, so which suggests that there might be the plantation of trees after this period of time. Regarding the codes, we'll try to go through the codes as much as possible, but it's kind of I think I personally found it kind of hard to understand because this is my first time going to this chapter. So I'll try to make it as quickly as possible. So this section deals about analyzing for the large areas. So we begin with the image collection. That's our main purpose. This is where we are getting this module for this purpose, and this module has these function within it to retrieve the clear Landsat observations. So this is required to filter any clouds, shadows, and any radiometrically exaggerated pixels. And then we have these parameters provided within this dictionary. So we have the breakpoint bands, T-mask bands, mean observations. So the authors have said that they have only changed the bands, update format, and lambda. So to understand few of them, so for instance, minimum observations is 6 year, which means that the number of these minimum observations means that the required number of consecutive observations to flag change. And we also have this chi-square probability 0.99 and minimum number of years scalar, which is 1.33. And these are the sensitivity of the algorithm to detect changes. And this try to fit the curve to detect change. So this is the iterative process. And this data equal to date format equal to 1 means we also consider the months within that year. And lambda is the scaling value to match the inputs. We have maximum iterations to control the curve fitting process. So the more we understand these parameters, the better we understand the CCDC. Applying this algorithm is easy. We have this function here, ee.algorithms.temporal segmentation.ccdc, and then we provide this dictionary for this function. And in this case, the result has already been exported. We can also see this this if provided to do this process, but this has already been done for our case. So this export results is false here. So if this is true, this process goes. And what if we print this, we see this image with multiple number of bands. So the authors have already done the process of exporting. So we have the path of the result. And if we print this result, we get this number of bands. So we have the start and end, T start and T end to say the start and end dates of each time segment. We have the T break, which means that the date, this is the time segment break date where the change was detected. We have number of observations, which means the number of observations used in each time segment. We also have change probability numeric value. So this is the change probability for each of the bands used for change detection. Then we have the coefficients for different regression coefficients for each of the bands in the image collection. We also have the RMSA for each time segment input band, and then we have this magnitude. So this is the time segment we detected changes, and some of the bands we can see that there it sets the 2 dimensions. So here this is a kind of array image, and we need to understand some array functions for proper manipulation. So here we have this time range that we can use. So we are generating a mask here that indicates the positioning array and the change probability to be 1. And when we load this layer, we get some kind of black and white image. So where the brighter means higher number of bricks, and bricks doesn't really mean that that change of landing cover has occurred. There can be some changes in the events or some kind of seasonality going on. or this is just to say that the brighter places will have the higher number of bricks, just to visualize. We can also visualize the first and last time, first and last time when the brick was recorded. And the other thing is here is the array marks somewhere. So this is the array marks to keep only the change states that meet our condition. So this function array paths fields or path those pixels that did not experience any changes, therefore have no will not have the value in the tree break band. And we also select the first and last values in the arrays. First and last values in the array and convert these image 1D array to regular image. So what we're doing here is that we are just trying to select those bands and try to visualize and trying to understand what these really mean. Then we have the magnitude bands to visualize where or when the latest changes have occurred. So we use the magnitude of change in the SWIR band, mask it and pad it in the same way before. And when we see this, this one is the first change and the last change. So the images detects break for the study area, and the darker means the recent dates, and the brighter means the older dates. So the first change layer means the clear patterns of some kind of expansion closer to 2000, and the last change layer shows recently detected and noisy breaks in some areas. So we also take the absolute values, magnitude in positive and negative. So positive value means there might have been some forest loss, and so the surface reflections goes from low to higher. And we are also finding the maximum absolute values, where we find the position on array and use that index to extract the original magnitude value. So this is the section 3, and we move to the section 4, where we try to extract the change information. We have the coefficients of time segments, and in this time segments related to time segments, we also have the harmony function with intercept, slope, and sine and cosine terms to represent the seasonality. And we have the coefficients and RMSE obtained by predicted and actual answer values. And we just try to retrieve the intercept coefficient for segment intersecting some specific dates. When we expand the bands in the console, we have the start, end, anti-end, and SWIR coefficients. So these are the array images containing dates when the time segments start, and we also have the time segments, date time segments, and coefficients for each of those segments. So the important thing here is that the segment, we are trying to find the segments that intersects at the given date. So here we have the target date as 2005.5, and we are trying to find the segments that meet the condition of starting before and ending after that date. So this will have the value of 1 and 0, and we're also selecting the array image. coefficient of SWR bands. So this will be the position where condition is true, and we use that to extract coefficients only for that segment. So here, to understand, we are trying to again use the coefficients and use the intercept coefficients and display it as the layer. Then we have the section 5, where we try to extract coefficients using external functions. So we extract the set of multiple coefficients and bands and try to use as the inputs to other workflows, maybe the classification. We extract and visualize the different coefficients for single date. We are producing the RGB image here. And we determine the date of interest and convert the CCDC results. So we get the array images, and we convert the array images to regular multiband images for easier manipulation, and also for the fast display. So we have the dates of interest here, and then we convert the date and as the bands for the CCDC. And then we have the list of lengths, maximum number of time segments to drive or the pixel. So we have the bands, we have the time segments, and we extract the subsets of coefficient for desired bands. And what we get is we get the date which we want to extract from it. We want to extract coefficient. And then we also have the list of segment names and the multiband images. And then we extract the slope and RMSE. And then we have displayed the 3 different layers. So slopes will have high values. They will be bright, and the last positive values will be dark. So this is for the slope and RMSE, where the slopes with high positive values will be bright, and last negative values will be dark. Then we have the RGB image for the middle point of time. This is similar to the composite image. So again, this is again to work with some array images and try to extract the coefficients from the bands, and maybe in the specific period of time. So this CCDC algorithm is useful for many purposes, made for studying deforestation, for preparing the classification, and it also captures the signal patterns. It is it requires the computational resources, and the author suggests to go towards the ensemble approaches where we do the multi-sensor analysis. So this was the maybe not good attempt to explain some of these some of the codes in this chapter. We certainly require multiple revisions. I just tried to go through the codes as much as possible, but there's certainly so many things to learn, and hopefully we will do this in future, and we will come back to this chapter again. Thank you for watching.